students, now we'll discuss electrophilic substitution reactions of phenol. We can write the resonance structures of phenol as like this. Already we have written such type of reactions. So because of the electron donating nature of this OH group, electron density is more in ortho as well as para position, and these canonical structure, resonance structure, second, third and fourth indicates the electron density, increased electron density in the ortho as well as para position. Now let us see why phenol is more reactive than benzene. From the above structure, it is clear that OH group donates a pair of electrons to the benzene ring. Hence, electron density on the benzene ring goes on increases. This attracts electrophile. That is E plus. Attracts electrophile E plus more strongly towards the ring. It attracts E plus more strongly towards the benzene ring. Hence, phenols are more reactive towards electrophilic substitution reaction. But in benzene ring, such type of groups are not present. And OH group increases. This OH group increases the activity of benzene ring towards electrophilic substitution reaction by donating pair of electrons. Hence, it is said to be OH group is said to be activating group. And also, as the electron density is more in ortho as well as para position, and it is also called as ortho and para directing group. As OH group increases electron density in the ortho as well as para position, and it increases the electron density. Hence, the electrophile are more strongly attracted towards benzene ring. So this is also called as activating group. And the electron density is more in ortho as well as para position. Hence, it is called as ortho and para directing group. Now let us discuss nitration reactions of phenol. Okay, first, phenol is treated with dilute nitric acid. This is phenol. When phenol is treated with dilute nitric acid, this acid should be dilute at 298 Kelvin temperature. You are going to get a mixture of OH, NO2. This is orthonitrophenol plus paranitrophenol. OH in para position, NO2. This is paranitrophenol plus 2H2. As this OH group is ortho as well as para directing, so incoming electrophile NO2 plus attacks ortho and para position. You are going to get a mixture of ortho and para products. Here, ortho and para products can be separated by steam distillation. This mixture can be separated by steam distillation. This mixture is separated by steam distillation because their boiling points differ with each other. They differ with the boiling points. Orthoisomer involves intramolecular hydrogen bonding. Whereas The paranitrophenol involves inter intermolecular intermolecular hydrogen bonding. Intermolecular hydrogen bonding. Intra means within the molecule. Within the molecule you are going to get hydrogen bond. Intra means within the molecule. Inter means hydrogen bond is formed between the two molecules, neighboring molecules. So as here association of this molecule takes place, so more energy required to break more number of hydrogen bonds, so its boiling point is more. But here in case of intramolecular hydrogen bonding, only one bond is formed between oxygen atom of NO2 group and hydrogen atom of OH group, so it is less energy is required to break one bond. This is orthonitrophenol. Here intramolecular hydrogen bond takes place means the hydrogen bond between the oxygen atom of NO2 group and hydrogen atom of OH group. So here this bond is formed within the molecule. Such type of bondings are called as intramolecular hydrogen bonding. So less energy is required to break this OH bond, hence its boiling point is less. But in case of paranitrophenol, association of molecule takes place. Here one molecule links with another molecule through this hydrogen bond. This is intermolecular hydrogen bonding. So more number of molecules are linked together. So more energy is required to break more hydrogen bonds. So its boiling point is high. Its boiling point is high. Its boiling point is low. Hence we can separate them by steam distillation. By steam distillation we can separate orthonitrophenol and paranitrophenol. Next reaction, when phenol is heated with a mixture of concentrated nitric acid and concentrated sulfuric acid, that is known as nitrate mixture. Mixture of concentrated nitric acid and sulfuric acid is known as nitrate mixture. We are going to get 2,4,6 trinitrophenol, that is commonly called as picric acid. If dilute nitric acid is used, you are going to get a mixture of ortho and paranitrophenol. If nitrate mixture, such as that is mixture of concentrated nitric acid and concentrated sulfuric acid is used, all the three positions in the benzene, that is 2 ortho and 1 para, that is 2,4,6 positions are occupied by NO2 group, that is known as 2,4,6 trinitrophenol called picric acid. This is the reaction. Phenol when treated with a nitrating mixture, this is concentrated, and here also you have to use concentrated H2SO4. Heat this mixture, all the three positions, this is 2, 4, 2, 4, 6, all the positions are occupied by NO2 group, that is known as picric acid. OH, NO2, NO2, NO2. This is 2,4-trinitrophenol picric acid. Picric acid and plus 3H2O. If strong conditions are used, yes, this all the three positions 2, 4, 6, 2, 4, 6, 2, 4, 6 trinitro. This moiety is phenol. You are going to get 2,4,6 trinitrophenol. Picric acid can also be prepared by the following two steps. In the first step, phenol is treated with concentrated sulfuric acid. Phenol is treated with concentrated sulfuric acid. Phenol is treated with concentrated sulfuric acid. You are going to get phenol 2,4-disulfonic acid. Phenol 2,4-disulfonic acid, SO3H plus 2H2. This is phenol 2,4 disulfonic acid. Phenol 2,4 disulfonic acid. In step 2, phenol 2,4 disulfonic acid is treated with nitric acid, to form picric acid. Phenol 2,4 disulfonic acid is treated with concentrated nitric acid. You are going to get picric acid. Picric acid. OH, NO2, NO2, NO2. This is picric acid. Picric acid plus H2 plus 2H2SO4. This is one more method of preparation of picric acid starting from phenol. Either phenol is treated with nitratic mixture to get picric acid, and picric acid can be best prepared by this method. First, phenol is converted into phenol 2,4 disulfonic acid on treatment with sulfuric acid. Then treat this 2,4 disulfonic acid is treated with the nitric acid. You are going to get 2,4,6 trinitrophenol, that is known as picric acid. Now we'll discuss hallucination reaction, that is bromination of phenol. Bromination of phenol. When phenol reacts with bromine, phenol OH, this is phenol reacts with bromine in the presence of inert solvents such as carbon disulfide CS2 at low temperature such as 273 Kelvin, you are going to get a mixture of orthobromophenol and parabromophenol. Orthobromophenol and parabromophenol. This is parabromophenol plus 2HBr. When phenol is treated here, phenol is treated with bromine in the presence of inert solvent. If phenol is treated with the bromine water, you are going to get phenol is treated with the bromine water, Br2, you will get OH here, Br 2,4,6 tribromophenol, 2,4,6 dash tribromophenol plus 3 HBr. This is phenol. Yes, here there are two reactions. In one reaction, we are going to get a mixture of ortho and parabromophenol. In another case, we have got only one product, that is 2,4,6 tribromophenol. Now let us see why there is difference between these two reactions. Here, bromine water is used. In the presence of water, phenol forms phenoxide ion. Phenol, in the presence of water, phenol forms phenoxide ion, which is more electrophilic than phenol. This is more phenoxide ion. This is more electrophilic. More electrophilic than phenol. More electrophilic than phenol. Hence, here this bromine water is used. Phenoxide ion is found. More electrophilic in nature. Hence, you are going to get 246 tribromophenol. 246 tribromophenol. In the absence of water, here inert solvent is used. In the absence of water, such as or inert solvent such as carbon disulfide is used at lower temperature. Phenol is less reactive. Phenol is less reactive. So we are going to get ortho as well as para substitution product. Ortho as well as para substitution product. That is the first point. And second point, due to the activating nature of OH group, due to the here OH group is activating, due to the activating nature of OH group, due to the activating nature of OH group, halogens reacts with phenols even in the absence of halogen carrier, even in the absence of halogen carrier such as FeCl3, FeBr3, etc. Because this OH group is ortho and para directing as well as activating group, so halogens does not require halogen carriers such as Lewis acid such as FeCl3, FeBr3, etc. This is about the halogenation of phenol. Now we'll discuss about Kolbe's reaction. When sodium phenate is heated with, first we'll write that reaction, how sodium phenate is formed. Phenol is treated with sodium hydroxide. This is phenol. When phenol is treated with sodium hydroxide solution, you are going to get sodium phenate, that is ONA minus H2O. This is sodium phenate. Okay. Then this sodium phenate is heated with carbon dioxide. Sodium phenate is heated with carbon dioxide gas at temperature 413 Kelvin, 413 Kelvin under 6 to 7 atmospheric pressure, sodium salt of salicylic acid is formed, that is sodium salicylate, OHCOONA, sodium salicylate is formed. Okay, sodium salicylate is formed, which on acidification, which on treatment with HCl, you are going to get salicylic acid. You are going to get, this is OHCOOH. This is salicylic acid. This reaction is known as Kolbe's reaction. When carbon dioxide is bubbled through sodium phenate solution at 413 Kelvin under 6 to 7 atmospheric pressure, you are going to get sodium salt of salicylic acid, that is sodium salicylate, which on acidification gives salicylic acid. And this reaction is known as Kolbe's reaction. Here you have to remember two more points. Here, if two acidic groups are present, then the salt of stronger acid is formed. Here OH, this hydrogen is also acidic, and the hydrogen of COH group is also acidic because this is salicylic acid. Here, if sodium salt is there, it forms salt with stronger acid. Then second point, if temperature is maintained more than 413 Kelvin, instead of orthoisomer, you are going to get para-isomer. You are going to get para-isomer. You have to remember these 2 points. If here the sodium salt of phenol is formed, whenever the salicylic acid is formed, then the sodium salt of salicylic acid is formed. Here you have to write OH and here you have to write CON. If here ON and here COH is written, then you are going to lose mark for that. This is about the Kolbe's reaction. Next is Reimer-Tiemann reaction. When phenol is refluxed with sodium hydroxide and chloroform CHCl3 at 333 Kelvin, you are going to get sodium salt of salicylic. You are going to get sodium salt of salicylic, which on acidification treatment with the dilute acid, which on acidification with dilute hydrochloric acid gives salicylic. This reaction is known as Reimer-Tiemann reaction. This reaction is known as Reimer-Tiemann reaction. Now let us discuss reaction part. Phenol is treated with CHCl3, chloroform and aqueous sodium hydroxide at 333 Kelvin. Here first you are going to get intermediate, that is substituted benzyl chloride. This is substituted benzyl chloride. Here UNA CHCl2. This is intermediate compound. This is substituted benzyl chloride, which when treatment with the sodium hydroxide, you are going to get ONeCHO. This is sodium salt of salicylic. Sodium salt of salicylic, which on acidification, which when treated with HCl, you are going to get salicylic. You are going to get salicylic. OHCHO. Salicylic. This reaction is known as Reimer-Tiemann reaction. This reaction known as Reimer-Tiemann reaction. Phenol when treated with chloroform and aqueous sodium hydroxide 333 Kelvin gives an intermediate, that is substituted benzyl chloride. Substituted benzyl chloride, which reacts with sodium hydroxide to form sodium salt of salicylic, which on acidification gives salicylic. This reaction known as Reimer-Tiemann reaction. Now we'll discuss a reaction of phenol with zinc dust. When phenol is heated with zinc dust, zinc powder. When phenol is heated with zinc dust, you are going to get benzene. Zinc dust, you are going to get benzene. Here H, this OH is replaced by H. This is benzene, or you can write like this. This is benzene plus ZNO. This reaction involves cleavage of carbon-oxygen bond. Cleavage of carbon-oxygen bond. Okay. Phenol is treated with zinc dust. This OH group is replaced. Carbon-oxygen bond gets cleaved. This is the only reaction where you can break up the carbon-oxygen bond. Carbon-oxygen bond. So phenol, when heated with zinc dust, it gives benzene. It gives benzene. Next reaction is oxidation. When phenol is oxidized by using chromic oxide H2CrO4 by heating it with oxidized by using chromic acid. This is chromic acid. It undergoes oxidation. You are going to get compound benzoquinone plus 2H2O. Here the phenol is converted into benzoquinone. Quinone is conjugated diketone. Quinone is conjugated diketone, and hence a colored compound. And hence is a colored compound. This is a colored compound. Hence is a colored compound. This is formed, or benzoquinone is also formed when phenol is exposed to air. If it is exposed to air, phenol is exposed to air, it develops brown color. It develops a brown color due to aerial oxidation. Benzoquinone is formed. Actually, phenol is colorless. If it is exposed to air, it undergoes aerial oxidation and form benzoquinone that develops a brown color. This is the reason why phenol gets a brown color when it is exposed to air. Next reaction is acetylation of phenol. When phenol reacts with acetyl chloride or acetic anhydride, this is phenol. When phenol is treated with acetyl chloride, ClCOCH3, this is acetyl chloride, in the presence of pyridine catalyst, you are going to get phenyl acetate. Acetylation takes place here. You are going to get phenyl acetate, OCOCH3 plus HCl. This is phenyl acetate, or this phenol is treated with, either you can use acetyl chloride or acetic anhydride. When phenol is treated with acetic anhydride, CH3CO, this is acetic anhydride. In the presence of pyridine catalyst, you are going to get the same compound, phenyl acetate OCOCH3 OCOCH3 plus CH3COH phenyl acetate this is acetylation of phenol. Now we'll discuss acetylation of salicylic acid. Acetylation of salicylic acid. Salicylic acid on acetylation gives acetyl salicylic acid. This is also called as aspirin. Salicylic acid is C6H4 here OH and here COH. This is salicylic acid. Salicylic acid. Salicylic acid. Salicylic acid is treated with acetic anhydride. Salicylic acid is treated with acetic anhydride CH3 COO C double bond O CH3. This is acetic anhydride. Acetic anhydride. Salicylic acid is treated with acetic anhydride in the presence of catalysts such as pyridine. In the presence of pyridine catalyst, you are going to get acetyl salicylic acid. Acetyl salicylic acid. Acetyl salicylic acid. Here COH. Here OCOCH3. OCOCH3. This is nothing but aspirin. Aspirin, another name for aspirin is acetyl salicylic acid. Acetyl salicylic acid. Acetyl salicylic acid plus a molecule of acetic acid. This is acetylation of salicylic acid. Now we'll discuss some uses of phenol. First, it is used as an antiseptic. It is used as an antiseptic. It is used as an antiseptic and disinfectant. Disinfectant. Number 2, it is used as a preservative for ink. Used as a preservative for ink. Preservative for ink. Third one, it acts as a powerful antiseptic in soaps and lotions. As a powerful antiseptic, in soaps and lotions. Soaps and lotions. In the manufacture of bakelite. In the manufacture of bakelite. The manufacture of bakelite, which is condensation polymer of, this is condensation polymer of bakelite, is condensation polymer of phenol and formaldehyde. Phenol and condensation polymer of phenol and formaldehyde. Bakelite is used in making molded products. Making molded products such as handles on electrical and such as handles on electrical and cooking utensils. And also electrical equipments. Fifth one, in the manufacture of cyclohexanol, in the manufacture of cyclohexanol, and used as solvent for rubber, and used as a solvent for rubber. Next use, in the manufacture of pharmaceutical products, such as in the manufacture of salicylic acid, aspirin, salicylic acid, aspirin, methyl salicylate, etc. Methyl salicylate, etc. Next, in the manufacture of, it is also used in the manufacture of dyes, like it is also used in the manufacture of phenolphthalein, picric acid, etc. It is also used in the manufacture of Dettol. These are some of the uses of phenol. First, it is used as antiseptic or disinfectant, and it is used as a preservative for ink, as a powerful antiseptic in soaps and lotions, in the manufacture of Becquerel, which is condensation polymer of phenol and formaldehyde. And Becquerel is used to prepare molded products such as handles on electrical and cooking utensils and electrical equipments also. Then it is used in the manufacture of cyclohexanol, used as a solvent of rubber. It is used in the manufacture of salicylic acid, aspirin, methyl salicylate, etc. It is also used in the preparation of phenolphthalein, picric acid, and even in the preparation of Dettol. This is about the chapter phenol.